what we're talking about now, and we go for the next few lectures, is a problem you might have thought, why the heck wasn't this? We talk about this when we first talk about quantum mechanics, because this seems like one of the most important problems in physics. The damped harmonic oscillator is something you would think you would talk about once you talk about the harmonic oscillator in quantum mechanics. But, you know, it's of course a little more complicated, the whole story of damping in quantum mechanics than it is in classical mechanics. But we'll kind of explore ways in which it's really the same and ways in which it's different, okay? And so the way we did this sort of from first principles is we went through the rigmarole of the Born-Markov approximation and the derivation of the master equation from system bath evolution and the Markov approximation and all of that. In the quantum optics, we typically are thinking about this kind of system bath interaction. We think about the mode of interest, which could be thinking about a mechanical oscillator or the oscillator that corresponds to the mode of the field that's interacting with a bosonic thermal bath, okay? So there's a bath of other oscillators that form a continuum, ultimately. And that continuum is where the Markov approximation comes in, amongst other ways. And when we go through that in the standard way, we end up with a master equation. So the standard paradigm we have for this that we're interested in quantum optics is thinking about some mode, like the mode of a field in a Fabry-Perot cavity, which has a finite Q, a finite decay constant, and so, you know, we can think about it as it's a finite reflectivity or finite absorption, but right now we just think about it as a finite reflectivity, and so energy can leak out, and thermal photons at that frequency and vacuum fluctuations at that frequency can leak in, okay? And so when we have that physical system in mind and we do the derivation, we find this form of the Lindblad master equation. So this is the quantum optical equation that we have for the damped oscillator. And it involves two kinds of jump operators, ones that involve emission or loss of photons from the cavity. They are related to the annihilation of photons. And then there's also possibility of photons jumping into the cavity from the thermal bath, if there are thermal photons around at that frequency. And the rates here depend on the rate at which a photon, in the absence of anything else, would leak out, and the number of thermal photons in the bath. So here, n bar is the number of thermal photons in the bath, and that's the Planck spectrum. At zero temperature, or if the temperature is sufficiently low compared to h bar omega, then this is effectively zero. So at room temperature, at optical frequencies, there's no optical photons around. But if, you know, we have a transition that's like a microwave, then we really have to worry about that, okay? At room temperature. Right. So this is the form of the master equation, and it's a master equation that we use all the time in quantum optics. Wilson lives it every day.
So real quick, okay, so let's say the cavity is optical.
Yep.
But the thermal is at 300K, which is room temperature. Those can be 10 microns instead of half a micron. So they don't contribute.
Yeah, right. So then we would set n bar to 0.
Okay. Got it.
And but nonetheless, even if for all intents and purposes, the bath is at 0 temperature, there's still vacuum fluctuations, and they mean that the system will interact with the bath in a way that causes this irreversible decay. And so we talked about this last lecture in looking at the rate equations. So if I take this equation and I ask what is the population in the nth oscillator state, for the case of the cavity, that corresponds to the state of the field with n photons in it. And I want to know what's the probability of having n photons in the cavity, right? So P sub n here is just another name for, nothing left to lose, no. It's another name for the diagonal matrix element of the density operator. And so it's the population in that state, which is the number of, say, the probability of having n photons in the cavity. Or for the mechanical oscillator, the probability of having n quanta of energy excitation in the pendulum. And we get the standard rate equations, which just say that there's some population that can leave and go into neighboring, either having one less or one more photon through these jump processes, or we have feeding terms which feed this population by going from n plus 1 to n, or going up from n minus 1 to n. So these are the processes just drawn as kind of arrows, where the squiggly lines represent the spontaneous decay between these levels, and the solid lines represent the stimulated decay or absorption, which has the same rate as stimulated emission. And they depend, these rates here, which I've written here, so this rate is for these two guys, this rate is for this guy, okay? Excuse my horribleness. There's many ways I'm horrible. That they depend on where I am in the ladder. So it depends on n. It also depends on the number of thermal photons and bar, or the average number of thermal photons. And that made sense, right? I mean, we're higher up in the ladder, there's more photons, so the rate at which it's going to decay is n times bigger, right? That's what this says, okay? Now, that's the rate equations. We can also look at the expectation values, right? And to do that, the most straightforward way is not to write down all the probabilities and then sum them up, is to just look at the equation of motion directly for the expectation value, which we can get by saying that this is equal to the trace of A with d rho dt, okay? So that's how the expectation value evolves in time according to the Schrodinger picture. And when we plug that in and rearrange with the cyclic property of trace and all of that, we get this equation of motion for how the expectation value evolves. So now to come to your question, Ivy, this first term is the term that comes from the Hamiltonian that I didn't write down.
But that's the.
There's an equal sign here that shouldn't be there.
Unless.
Oh, sorry, that shouldn't be there. That equal sign, excuse me, yeah, yes, I'm sorry. Yes, I didn't, it's one of these things I write that I don't see, but.
But would it be true that there's a relationship between that Hamiltonian commutator, if the only Hamiltonian term is the interaction Hamiltonian and you trace over the external degrees of freedom?
Yeah,
Can you make that jump in that case?
So what is true is that the expectation value would generally involve the whole Hamiltonian, the Hamiltonian for the system, the Hamiltonian for the environment, and the interaction Hamiltonian, and we do that trace over. But this piece already is that, okay? So this piece is just the system Hamiltonian. The system in this case is the one mode of the oscillator. That's the system we care about. Everything else is the environment. So what I'm saying is the evolution, as we've said before, generally, I could write, as we wrote for the master equation, is the Hamiltonian part plus the dissipative part. That's what this thing is, okay? So this is the effective evolution of the state after we've done all the trace over the environment, made the Born-Markov approximation. There's a part that's the Hamiltonian evolution, and then the part that had to do with the coupling to the environment. And after we did all the rigmarole, we get the Lindblad equation. What this is just plugging this in and rearranging terms. And the point of it is that I can get a kind of generalization of the Ehrenfest equation. The Ehrenfest theorem you're often taught is about how expectation values of observables evolve and their relationship to the standard Hamiltonian evolution. There's another term in it which is the coupling to the environment, if that is lumped in some of this effective way, okay? And that's just from plugging in the master equation and rearranging, but this expectation value is the trace of this thing with the density operator of the system. Okay, so using that equation, we find equations of motion for, say, how the mean photon number in the cavity and how the mean amplitude of the mean field decays or changes as a function of time, okay? And we get this equation of motion for the photon number, and that's an equation we can just look at and know the solution to. Whatever the initial photon number is decays, and then it comes to steady state, and the steady state is equal to the thermal state. So in steady state, the cavity is populated with a thermal number of photons. If that is approximately 0, then it goes to the vacuum, okay? The mean amplitude, if we say started with a coherent state or something that had a mean amplitude, then its equation of motion, well, whatever it is, this is the equation of motion, but this is how it evolves as a function of time. And this is equivalent to the classical equation of motion we would expect for a classical oscillator. And in phase space, what we would say is, there's the real part of alpha, which is, the x quadrature over root 2, and the imaginary part of alpha, which is p over root 2, and I'm putting in the root 2's for emphasis. Then if we start at some point here, then what we find is the amplitude will not just oscillate around, but it will decay and go to 0. That's classical motion of a damped simple harmonic oscillator, okay? And so, again, the harmonic oscillator is in some ways very classical. The equation of motion for the mean field is completely classical. No matter what the state is, the mean will evolve according to the classical equation of motion, no matter what the quantum fluctuations are around it. Okay? Now, this is where we were last time. And we were left with a bit of a paradox, because interestingly, this equation is linear. It also has no dependence on n bar. It's not that I set n bar to 0, it's that once I do that commutator, I'm just too lazy to do it on the board. You find this equation, and it has nothing to do with the thermal number of photons. The mean decays this way, but most importantly, it's a linear equation, which means that the rate at which this thing decays has nothing to do with how the harmonic oscillator decays to 0 at a rate that is independent of the amplitude. Okay? It doesn't depend how much energy I put into the oscillator. The rate at which it goes back to being at 0, if there's friction, has nothing to do with how much it's swinging. And that seems in contradiction to this picture where we said the energy, how much energy decays out of this, each one of these levels, depends on how excited that was. And that seemed to make sense because there are more quanta of excitation, and therefore there's more ways in which there's n different quanta that can, so there's something hinky going on here. How is that, how can these two things both be true at the same time? And the answer is something very special about the harmonic oscillator, having to do with the idea of the transfer of coherences. So the question is, why does coherence? So this, remember that something has a mean field because there's a superposition of states with different numbers of excitations, right? If something had a definite number of excitations, this would be 0. It's only coming from, this arises from the coherences. Maybe I'll just write that out for a moment. If I wanted to ask what this, I have a density matrix. So the expectation value of A is the trace of rho with A, right? And if I can write that as the sum of the diagonal matrix elements, right? But this is the square root of n times rho n minus 1, right? So this is an off-diagonal element, which we call something that has to do with what we call a coherence. It has to do with the fact that there's a superposition of n and n minus 1. There's some, it's not just a diagonal matrix element, but it has off-diagonal matrix elements. So the mean field depends on how big the coherences are. So now the question is, why does coherence decay? Why do we lose coherence when the system is in contact with the environment, with the reservoir? Well, the reason is because the environment becomes entangled with the system. And in some sense, we say that the environment has which-way information. Which-way information is a jargon for thinking about, you know, an interferometer. Did it go this way or that way? Do I have a superposition of, is it in this path or that path? And we lose coherence because something knows which way it went. And if something knows which way it went, then we lose coherence, okay? So that's really important. That is to say, informally, we see that by the system, if the environment, whatever other degrees of freedom become correlated with which path, then the environment is entangled. And once we trace that out, the system becomes mixed, right? So we lose the coherence because the environment has which-way information. And it has which-way information through entanglement.
But just to be clear,
Yeah.
optical coherence is interference.
It is.
Yeah, okay.
Yes,
Just want to be clear.
it's the same thing.
Yeah.
And so is quantum coherence. Quantum coherence is interference between probability amplitudes. So coherence is the capacity of the system to show interference.
Yeah.
And we lose that capacity when the two amplitudes, the two possible amplitudes, whether they're classical amplitudes or quantum amplitudes, when they become dephased, and they become dephased in this context through entanglement. Now, the question is, what's entangled here is, okay, there's something in the environment, which is to say there's some information in the photons that have leaked out about whether it was in one level or another. So let's just say that I had, let me write this a slightly different way, just because it doesn't really matter. Let's say I had some superposition of this level and that level, okay? So there's some coherence here. There's some off-diagonal matrix element between here. Let's just, for simplicity, just treat the case where n bar is 0, where there's no absorption or stimulated emission. It doesn't, in the end, in this case, it doesn't matter, but it's just easier to discuss from that. So this level can decay here, and that level to decay here, right? And then I would have, in that case, potentially some superposition between n and n minus 1. The question is there any information about whether it came from here or here in these photons? Well, yes and no. Importantly, there's nothing about whether, there's no way to know whether it's this photon that, the photon that I see that leaked into the cavity, I can't tell whether it came from this transition or that transition because they have the same frequency. They have the same polarization. There's nothing distinguishable. They're indistinguishable photons, so I can't tell whether, if this transition happened or that transition happened. And to the degree to which there's no information about which transition happened, this coherence would be perfectly transferred. I would transfer the coherence from this superposition to this superposition. That's true for the harmonic oscillator because of the fact that these are equally, if this was an anharmonic oscillator, this wouldn't be true. Come back to that. Now, why did I say, well, if that were true, if what I said was exactly true, and it is, but there's one thing I left out, then the coherences wouldn't decay at all. And they do decay, otherwise the thing would maintain this coherence and there would be no decay of the mean field. So why does it decay at all if there's no information in whether it's this photon or that photon?
The rates are different?
Sorry?
The rates are different?
That's right, exactly. So if it happens, it's more likely it came from here because this one happens more rapidly than that. But there's still a big cancellation in the fact that there is this transfer of coherences. So we can see this formally, let's just write it down, by writing down the equation of motion from using this for how the coherences decay. And what I get is the following. Where's this is pen I want. So just for simplicity, let me just go into the rotating frame. Just forget about this. I'm just going to set this to 0, so I don't have to worry about the Hamiltonian part. I'm just interested in dissipation. And what do I get is the following. I'm going to also look at the case for n bar equals 0, but you can look at the notes, and there's a more general case, but I don't want to. I want to just focus on the most important part here. So what I find using the master equation is equations of motion for how the coherences evolve, and I find the following. So firstly, I have a term that looks like these coherences decay by an amount that depends on where I am. However, importantly, what I have is this term. No, sorry.
So you said the gammas are different, but now you're only using one gamma. So
Oh, excuse me. Let me, no. There's one gamma, one parameter gamma, but what I'm saying is that the rate at which this decays depends on it.
Oh.
Okay, so there's one parameter gamma, but what I see here is that the rate at which this thing decays
Okay.
depends on where I am in the ladder. However, I have this term, which is called the feeding of coherences. Typically, in an open system, coherence just decays, there's nothing that feeds it. What feeds the coherence is typically driving with the coherent source, like, if I had a laser that I'm pumping this with, then I would drive coherence in here. But if I don't have that, typically there's nothing that feeds the coherence. But in this problem there is, because of this fact. So there's a feeding from n plus 1, n plus 2. These guys feed this. This coherence feeds that coherence. And that feeding term is what ultimately cancels this n dependence. And if I plug that in to this expression that I wrote down for the average A, I get that, the mean amplitude I just relabeled things a little bit. It was easier this way. And what I get in this problem is the following. You can look in the notes. So that's from the decay term. And then I have the feeding term, and the feeding term looks like this. And these cancel. It's very interesting. So now, I want to ask you the following question. Suppose I had a slightly anharmonic oscillator, okay? So I'm gonna have my harmonic potential, let's think a particle in the well. I have a harmonic oscillator, and then I have some x to the fourth. okay? So, sort of depends how big this term is. Let's say this is tiny. The fourth order curvature is small compared to the second order. So I have something that is, this is my harmonic oscillator, and it's very slightly anharmonic. Okay, so it's slightly flat on the bottom, okay? And now my levels are not exactly equally spaced. This is slightly different, you know. This is gonna be omega naught. This is gonna be omega naught plus some small delta omega, depending on, I could do perturbation theory if I wanted to see how much it shifted, for example. So now I don't have the exact transfer of coherences. Now, I do the same coupling of the system and the environment, coupling is still the same. But this problem doesn't have the exact transfer of coherences because now I have this delta omega here, but the master equation that we wrote down has this transfer of coherences. So I might have said that, you know, my master equation is, you know, I have the Hamiltonian, which has, you know, p squared over 2m, the harmonic oscillator term, which I might write as, you know, a dagger a times omega, and then I have, you know, some kappa, something like a dagger a squared, and then L dis. This is how I might treat an anharmonic oscillator that's decaying, where I just included the same coupling to the environment. But was that fair? I mean, should the way in which the system Hamiltonian changed, and does that change the nature of the jump operators, and shouldn't it? Because with these jump operators, we had transfer of coherences, but it seems like we should have lost the transfer of coherences. So this is a debate I've been having with people over the years, and it's a constant source of confusion. I had this recent conversation with Victor Albert at the University of Maryland about this. Okay, so firstly, I would say it would seem to me to be intuitive that there should be some kind of continuous limit of this, right? I mean, if kappa goes to 0, then we have what we just started. If kappa is somehow infinitesimally small, it shouldn't mean that the whole master equation was wrong. But the effect of that should show up somehow. And the point here is that there's two different ways to approach this problem. So here's the question. Under what condition would you say that this delta omega is important? It would be important to the degree to which that delta omega allowed me to distinguish this photon from that photon. Now, these photons aren't initially, I can't tell what frequency they are unless I have enough time to see enough oscillations to know, to distinguish two different frequencies. If the frequencies are very close, who cares? From all intents and purposes, there's no information there because I haven't had time to find it. And So the decay of these coherents is also a temporal process which would happen in some combination of these two. I don't really have to include this in the dissipative. I can include it in the Hamiltonian part and see dynamically when I would lose those coherences or not. And the only way I could see this difference is if I have enough time to do it.
So that's the energy time uncertainty.
That's one way of saying it. Another way of just saying it is there's no way I can tell the difference between this, you know, and I can't draw it, that unless I've got enough bases I can tell the difference between them. But that will depend on how long the lifetime is, right? So if this is much, much smaller than gamma, then who cares? There's no way, right? So the question is, how big is this anharmonicity compared to the line width, right? Once this gets big compared to the line width, well, at that point, then I'll be able to tell the difference between them, and then I'll lose those coherences. But that will show up in the dynamics. I don't have to have different jump operators associated with the different frequencies. I could. It's a much messier problem, but I don't have to modify the jump operators. And this is just a general question. We talked about the two-level atom. And we said, oh, this guy will spontaneously decay. And it spontaneously decays at a rate gamma. Now I'm going to shine a laser on this atom, which is very good, has very good coherence and is at a good frequency, and I tune it, say, right to resonance. And there's some Rabi frequency that's associated with this. We derived, with me waving my hands a lot, the master equation for the two-level atom, excluding the laser. We just had the two-level atom as the system, and we had the vacuum, and I did the trace, and I did all the rigmarole, and we found that. Is it fair then to just say that the density matrix of this is where H, is the usual kind of thing, without modifying the way in which this thing spontaneously emits? That's what we do all the time. We just say, there's the master equation for the atom decaying in the layer, and then we just add in a Hamiltonian after the fact. But the Hamiltonian, in principle, should have been part of the derivation of the master equation. So why was that kosher? Because it is completely excellent approximation to do that. Anyone have a thought? Well, I know you have thoughts, but yes, I'm listening.
Might it be related to linearity in the weak field limit?
Linearity is part of it. What's the other part?
In the weak field limit?
Weak field. So I think that's a component of things. But there's another sort of important aspect of which is interrelated to what you were suggesting, which really has to do with time scales. Remember our whole business about delta T, the coarse graining, was supposed to be absolutely huge compared to TC, and when we didn't have the driving, we said this was related to whatever the relaxation time. But really what's important here is not just the T electrician, but I would say is the T system dynamics. So as long as this flopping is happening on a time scale which is incredibly long compared to the time scale over which the system and reservoir become decorrelated, in which they retain coherence, then moving this up and down between it doesn't matter. So it's sometimes called the secular approximation in this, and it's swept under the rug. You derive the master equation just assuming the system is undriven in any way. You find how it decays, and then you just add driving in willy-nilly. You just say, plug it in. And you don't typically worry about how it affected the distributive terms. But there's a approximation hiding beneath that, which is that your driving doesn't break the whole Markov approximation. And it's similar for this problem. The question is, how big is this anharmonic term compared to the correlation time with the reservoir, which is very, very small? Yeah?
It seems like another reason I'm thinking why that approximation is valid is that when we have the laser, we don't expect that to change the form of the atom-environment interaction Hamiltonian. Whereas if we're thinking about an anharmonic oscillator, we really can't have the same, you wrote it down, so I'm not going to give you the board. You can't have the same, interaction Hamiltonian, because
Why
that
not?
doesn't respect conservation of energy as the sum of energy in the system and environment.
But this is the way in which this actually has nothing to do with the nature. This is just a beam splitter interaction.
Well, it seems like that runs afoul of energy conservation, because this is saying, okay, we jump, down one level in the system, and that's going to lose some energy omega plus some delta omega, and we're going to jump up in the environment, which is going to gain some energy omega. So this seems to run afoul of energy conservation. Like, depending on what level you're at, when you
But
go
it's
down.
just those aren't the right levels anymore. The levels are different levels. I mean, this Hamiltonian alone doesn't have to conserve energy. It's the total energy of the system is the energy the total energy of the universe is the energy of the system, the energy of what we're calling the environment, and the interaction Hamiltonian. This interaction Hamiltonian has nothing to do with the internal energy. This doesn't have to conserve energy. The whole system has to conserve it, which it will, because it would be the total Hamiltonian. And this really just relates to how photons, which hit the mirror, do something, how they leak out or leak in. And at the end of the day, the derivation of the master equation does depend not only on the nature of the interaction Hamiltonian, but also depends on whatever other Hamiltonians there are that we call the system Hamiltonian alone, or the environment alone, because when you go to the interaction picture, there'll be time dependence in these operators that depends on those other Hamiltonians. So I don't agree that the issue is about how the interaction is modified by that will in no way, the fact that if I put a Kerr system in here with a Kerr nonlinearity, that would in no way affect what photons do, how they leak out.
Well, shouldn't what mode in the environment gets raised, gets that V dagger, depend on what level you're at in your anharmonic oscillator? Because when you go down one level in your anharmonic oscillator, that's going to change the energy of the photon that you release. So you shouldn't say, you can't just put BK dagger because you're putting
really
energy
the
into
question
the
is,
wrong
what
level
does
in the
A
environment.
represent anymore?
So an operator that moves you between levels in your anharmonic oscillator?
I mean, the question is, do I call these the quanta of the free field or the quanta of the interaction or interacting field.
I guess I'm thinking of
Yeah.
them as the quanta of the anharmonic oscillator.
Right, but they're not. They're the quanta of the free field, and then we put, you know, you can dress things in different ways.
Okay.
But, you know, I don't want to go down this rabbit hole too deeply. It's just to say that in principle, and we can talk about this more, I'm happy to discuss this more afterwards. In principle, we should modify the master equation depending on the nature of the Hamiltonian. That's to say, of the system alone, and whether the system is this or that, or whether I have another external field driving the system. But in practice, we almost never have to do that. And the reason we don't have to do that is because typically the way in which we might modify the system will not affect any of the approximations that we made when we went to the interaction picture and all of that. So driving the system with a laser or putting in the anharmonic oscillator is not important. It's equivalent to just leaving that Hamiltonian term there. Well, was it your question?
So two questions.
Yeah.
One is it, can we just say that the environment doesn't have enough time to measure the energy of the photon, and that's why we can just do this?
Yeah, I mean, the question is, what's the decay rate compared to that energy difference, right?
Yeah.
And when that decay rate is much faster than that energy difference, we can't tell the difference. It's another way of saying, if I have two photons that are coming from slightly different energy difference, can I tell the difference between this and this? Well, it depends on the line width. If the line width is so big, I can't tell the difference between. That's in the frequency domain. In the time domain, I would say, what's the rate at which it decays compared to that? But if the line width is big compared to the difference between this and this, there's no way I can tell the difference between them. But that's, I mean, I'm saying this from an intuitive way. Mathematically, it comes out the same. Yeah?
More of a basic question. How would you, what like gives this kappa x to the fourth term? Like how do you make a harmonic oscillator?
An harmonic oscillator. So if I have, so this is known as the Kerr effect in classical optics, and I can look at it this way. It's saying that the frequency of oscillation depends on the amplitude.
I see. Okay.
So if I have a material whose index of refraction depends on the intensity, and not, then that's called the Kerr effect in classical optics. And it's a quantum optical thing that some people think about.
Thank you.
Yeah.
So I have another question.
Yes.
So if we include, let's say we only have Kerr effect, and instead of doing photon loss, in which we don't really know with, instead of doing this usual photon loss, we do that frequency dependent noise.
Yeah.
Will we still see, let's say the quantum to classical transition is dependent on the amplitude, for example?
I didn't quite get the question, Melissa.
So we, you know, all of this is just to say that photon loss is a good noise model, right?
It is. Yeah, it's a good model for the damped oscillator.
Yeah. I guess the question is, what if it's not? Like, how do we know it's not? Like,
What do you mean? How do we know? When would it not
when
be the
it's
case?
not, yeah.
Under what conditions would it not be the case?
Yeah.
I think it would require incredibly large nonlinearities
Okay, yeah. I
Yeah.
guess that's what
that are unphysical.
I see, okay,
Yeah.
yeah, that's.
We could. So one of my first students, I was so confused about this. You know, it's like, because you know that we looked at this 1984 paper by Milburn back in 2005 or 3 or whatever the hell it was, And it's like, well, how could we just add the Kerr nonlinearity into that? And so Andrew Silverfarb, God, he was amazing. Yeah, he realized that you could do it either way. And it's kind of interesting to see. So if you could rederive the master equation in the interaction picture, putting in the Kerr nonlinearity, you'll get a different set of jump operators. And you can show that the dynamics of that problem is exactly the same as this one. So you could have a different noise model, but you don't need to do that. And the only time it wouldn't be the same is if the Kerr nonlinearity were big enough to break the Markov approximation.
Yeah,
And
then if you break the
that's never
Markov
gonna happen.
approximation, then.
Yeah, it's never gonna
forget about
happen.
it.
Awesome, all right. Well, it's good, we're having a good conversation. We didn't get where I wanted to get, but you know, there's always next semester. All right. Yeah, Harmonic 3, your favorite. Let's though continue where, at least get to this one last thing I wanted to, at least one other thing I wanted to discuss with that. But we're gonna do a whole bunch more. But it's good. We're learning stuff. Okay. So what the heck was I gonna do? Oh yeah, that, right. So let's talk about quadratures. Okay, so we have our phase space here. And then I can think about any quadrature I like. Doesn't really matter. The phi is really not that important, but this is just sort of completely general in this sense of whatever quadrature I'm talking about. And I want to know how, when I have a damped oscillator, how do the mean quadrature and the fluctuations in the quadratures, which is to say the kind of, we think about, you know, something like a squeezed state, which has some fluctuations around the mean, what happens to the fluctuations when I have photon loss, okay, or photon gain from the black body. So I have this master equation. So we can do the same rigmarole here of calculating the mean, how the mean operators evolve according to this equation. Okay? And I'm not going to do the algebra. I'm going to say the recipe was done. You put it in the oven. It came out perfect. So let's see what it is. Well, some of them are trivial to see. I mean, we can just write down how the mean quadratures, once we know this, then we know the quadrature is just this plus this dagger. And so they decay the same as A and A dagger, which decay. Let's just, you know, I'm just going to go into the rotating frame and just set this to 0. So these decay independently of n over n bar. And the equation of motion for the square is equal to that. Okay? So again, these equations of motion follow from this general form, doing those commutators and putting it all together, okay? And so I can ask now, how does the variance change as a function of time, okay? Which is equal to how the square of the quadrature minus twice the mean times this. Okay. And so what do I get? Well, this is this. And so what I get in that case is, this is minus gamma delta x squared, right? Because that's what this is. Well, I plug that in, I get this, and then I get twice that squared, so I get minus of that, and then I get plus gamma n bar plus a half. Okay? So I ask you, what is the solution to this differential equation? How does the variance, how do the fluctuations in any quadrature change as a function of time? What is the solution to this differential equation? Something decays and then it comes to steady state. So whatever the initial guy is, it decays at the rate gamma, and then it comes to steady state. And what is the steady state? What's the fluctuate? If I set the right-hand side to 0, then this equals this, and thus this equals that. Okay? So, let's say that I had started with a coherent state. And let's say I have a coherent state. Then what are the fluctuations in any quadrature look like? What is this for a coherent state? 1/2, thank you. It's a half. Doesn't matter what it is, it's a half. So we have, the system has a mean field and it has equal quadratures in any direction. We can think about it as a figure function that's a Gaussian that is isometric. I mean, it's isomorphic, not isomorphic, but is angularly invariant. What happens over time? Well, ultimately, this thing will, let's firstly ask the question, what if n bar is 0? So I have a coherent state, and I have no thermal photons, and it can decay out of the cavity. If this is equal to a half, and n bar is 0, then what I find is that this at all times, this is at time t equals 0, is also a half. In fact, what happens is eventually, this is the vacuum. So this is alpha, and this is 0. In fact, one of the things we'll see in extra credit homework is that the harmonic oscillator is special in that if I start with a state which at time t equals 0 is a coherent state, and it evolves according to the master equation, with n bar equals 0, then the state at all times is pure. And it stays at all times a pure state, but it's just with the amplitude. It's always a coherent state, but its amplitude decays classically. It has exactly the same quantum fluctuations. There's lots of different ways of thinking about that. One way of thinking about it is the following. When I have n bar is 0, then my only Lindblad operator is the one for absorption. But my state is an eigenstate of the jump operator. And so it doesn't change the state in a certain sense. It does, obviously the amplitude, we're going to come back to that, it's a very tricky business. But the fact that the state is an eigenstate of that is what's sometimes known as a pointer state. We'll talk about that in the context of this theory of decoherence. The states that are eigenstates of the jump operators are kind of the most robust. They're kind of the things that are least affected by the jumps. Another way of thinking about why a coherent state stays a coherent state in the presence of photon loss is that this jump process is a Poisson process. And the statistics of the photons are Poissonian. So you're not changing the statistics, you're just changing the amplitude. Okay, what if n naught wasn't 0? Then what would happen to this thing? Well, what would happen is it would get a little bit chubbier, and ultimately my fluctuations in all directions would go to this. Is that what you expect? So in steady state, we know that the mean decays to 0. What is the state of the field that is the mode of interest in steady state? It's a thermal state. A thermal state, we can ask ourselves, what are the fluctuations in the quadratures? And the answer is this. When we do the problem of if my thermal state is e to the minus h bar omega a dagger a divided by the partition function, and I ask what are the mean quadratures, I get this. How would you calculate that if you didn't remember? There's lots of ways to do it, but the easiest way to do it is to use our friend, the Wigner function. Because the Wigner function, the means of the quadratures are just the average over that, and the Wigner function for a coherent state is equal to And if I take this and write in terms of x and p and calculate the quadratures, I find this is the mean fluctuation. Okay. This is actually the p function. That's what it is for. That's the Albert p. That's the bigger function. Very good. Finally, what if I had a squeeze state? So suppose I have a squeeze state, doesn't matter, squeeze state, for example, along the x quadrature. And I wanted to know what's going to happen here. How would this thing, well, we know the mean field is just going to still decay towards the origin with the same. What happens to the fluctuations?
They'll circularize and
They'll
approach.
circularize, right?
And approach the radius we expect for the temperature.
That's right. So let's just for the moment say that n bar is 0. We know in steady state it's going to be the vacuum. And it's going to, as you say, what's going to happen is this guy is going to shrink a little bit. It's going to become, in some sense, I lose squeezing. Photon loss is the enemy of quantum in the field. Why is, so this is, we see that from the mathematics here. So, as I lose photons, this state becomes more and more unsqueezed. It becomes more and more like a coherent state. It's lost its quantum properties. What physics can we attribute that to? Well, it really, again, has to do with what's going on in a loss process. In a loss process, what's happening is that you're randomly taking a photon out of the field. But we remember that squeezing involves coherence with photon pairs. Either one mode or two mode squeezing. When we had, so if I thought about a squeeze state, which we had some squeezing parameter R, we remember this business, right? The squeezing operator acting on the vacuum, right? And this we could write as something like, to lowest order for R much, much less than 1, we have the first, I can write this as the identity, and then plus R a squared minus a dagger squared, dot, 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 acting on the vacuum, which is the vacuum plus or minus, doesn't really matter, it's, the sign tells me which quadrature. And we had this coherence between the vacuum and two photons was critical. It's the interference between these that gives rise to something that can reduce the quadrature fluctuations below the standard quantum limit. But when I lose a photon, I just lose one photon. I don't have these photon pair, and that affects this. So these photon correlations, whether we call it part of entanglement or coherence, were critical to creating these non-classical features. And loss, if the loss would take two photons out together, that would be good. We can do that, yeah.
Is it the case, though, that the squeezing remains but falls into the correlations between the mode and the bath? That if one had more fine-grained access to the bath modes?
Yeah, I mean, of course, I think it's fair to say that, you know, it's kind of equivalent to saying, I won't get scrambled in the black hole if, you know, we can keep every piece of me and it's there, we can reassemble me. It's probably unlikely. I'd kind of like to do that journey, but, you know.
We all like to do things at least once.
If there's one thing you to do in your lifetime, to go through on the other side of the event horizon, I think that would be a win. But
It's a moot point, I get it.
but that's the point, yeah. And you know, I just would say that this is really one of the reasons why, you know, it's a real challenge for quantum communications and the ability to transfer quantum information over long distances is photon loss. So, you know, even in something as good as an optical fiber, you still have some loss. Now, of course, in optical fibers, you know, that's been developed over decades to special glasses that have a particular window of, you know, it's called the telecom wavelength, right? There's some particular wavelength, I don't even remember what it is.
155.
Thank you. 1.55 microns, right? Where, you know, you have incredibly low loss. You have some dispersion, and you can manage dispersion, but you have incredibly low loss. And so one of the things that people try to do is to devise ways in which you can transfer quantum information from something into a telecom photon. And then, you know, send that over, because then you have the least chance of loss. Because typically the, what, you know, where the wavelengths at which we might manipulate atoms, or even worse, things like superconducting circuits which happen in the microwave, there's no way you're going to send these microwaves over because there's all these thermal microwaves around. So the problem of transduction is a big problem. That is to say, you want to transduce a microwave photon into a telecom photon, or something about, you know, optical coherence in matter into a telecom photon. But, you know, there's one of the startup companies that's trying to do quantum computing is called PsiQuantum. They are trying to do quantum computing with photons, and, you know, they're keeping secret how they're going to keep photon loss at a minimum, but I can't imagine.
Do standard quantum error correction techniques not work against photon loss?
They will, but, you know, the question is what their loss is compared to, you know, it's all about the rates. It's all about the rates. I mean, that's the big hope, and what they're working on is, you know, specially designed codes that have that loss as the real dominant. You know, if you can think about biased codes that, you know, really concentrate on the photon loss, and that's the hope. But there's a lot of, anyway, that's a whole nother story, because, you know, in order to do quantum computing in particular with photons, requires you to say, how are you going to get photons to interact with one another? And that ain't so easy, but it turns out that we can use our friend the Hungel-Mandel effect. So you remember, even with linear optics, if I have two photons, I have this situation where they either go off the same direction or they're both reflected, but never one, right? You remember the Hungel-Mandel effect. And that is really a kind of nonlinear effect, even though it's linear optics, in the sense that it does something differently, whether there's 0 or 1 photons. But it's a random process, but if you do measurement and post-selection, then you can make a universal quantum computer just with linear optics, measurement, and feed forward, conditioned on the measurement outcomes. That was a huge surprise, and that is something known as the KLM scheme for linear optical quantum computing.
In a sense, all heavy lifting being done by your
Yeah.
students.
And if in quantum optics 3, we'll study this. I'm not
But you
kidding.
definitely have the syllabus.
I do. But you know, you have to do a tremendous number of these kinds of things for the post-selection and measurement. So there's another level of overhead when you don't have deterministic gates on this. But you know, venture capitalists are betting $1 billion on it. So.
That's because they just don't know.
I'm on YouTube, I can't say. Very good. All right, that was fun. Have a good afternoon. There's a really cool seminar happening in